recording.
Okay. So hi guys, this is a seminar about our research in ANPL. Vadim, do you want to say a few words?
Sure. So Roee is going to give a seminar about his M.Sc research. So Roee holds a dual degree, first degree in electrical engineering and physics. And he's been pursuing his master's degree in computer science since 2017. And he'll be talking now about qualitative SLAM. Go ahead, Roee.
Thanks, Vadim. So we'll talk about this research, the probabilistic qualitative geometry SLAM we are doing for the last few years. First, we'll just have a short introduction and motivation for the research. Then we'll talk about the general concept, and eventually we'll talk about the specifics of the research and our conclusions. Okay, so you all know, I assume you all know about the SLAM problem. SLAM is simultaneous localization and mapping. It means you have a map, which is a set of landmarks you can see in the environment, and you have a camera that makes a specific trajectory over time and measures these landmarks. And then the SLAM problem is simultaneously estimating the trajectory of the camera, which means 6 degrees of freedom of the camera over time, and then the location of the landmarks, which is the map. So the SLAM problem is well researched for more than 20 years. Today, SLAM is like used in actual real-world systems by academy and also by industry. And good results are achieved. For example, you can see the Kitty dataset example here. This is a vehicle just driving the streets, and you can see the estimation of the trajectory as well as the point cloud, which is the map, which is the set of landmarks that are being tracked. So SLAM in general is like useful, and today is in a level where you can use it in real-world scenarios, but it still has some challenges. One of them is that error is accumulated, okay, because of linearization, because of measurement noise, and SLAM over a long time can't hold a good position in a global frame. And then also there's the computational complexity of SLAM. So it can be partially implemented in low-level computing systems today, but like full implementation in real time is still not always possible. And also active planning is really expensive and not real time today. So the motivation of our research is that we just noted that when humans, for example, try to plan a path and navigate through an environment, they don't use this like traditional SLAM method. They do it a little differently. So for example, if I want to get from the start to finish on this map, I'm going to plan a path, and then the way I'm going to use this plan is I'm not going to know at each time metrically, like accurately where I am on the map, on the global frame. Okay, I'm just going to use landmarks I can track, for example, the hilltops or like other salient landmarks. And then while I'm navigating, I'm just going to reference myself to these landmarks I can see at each time. So it's like relative navigation. It's not going to be a global navigation to know exactly where I am on the map in each second. And also it's going to be qualitative because my plan is going to just go between like these first 2 landmarks and then go next to the 3rd landmark and so on. And I'm going to leave the specifics of the accurate like path choosing for other constraints. Okay, so I'm going to choose the specific path locally, just using the terrain and like where is easier to go through, and the navigation itself is going to be qualitative. So another example, when you see like the sport analytics on TV, the professional sport analytics, they try to infer like tactics and the position of a specific a player in reference to others. So they don't use a global frame to say metrically where each player is located on the field. They just use qualitative reasoning. Okay, they know if a player is behind the defense line or in front of the defense line and stuff like that. So we take these two insights and we try to make a SLAM framework, which is like using these two insights and just diverging a little bit from the traditional way to do it. So the first insight is using relative frames, relative to landmarks we see at each time. And then the other insight is using qualitative geometry. Okay, for example, you can see here a space partition, which is called the double cross. So if you have two landmarks A and B, then you can say that something like a third landmark or a camera is left of this line generated by A and B, and it can be before B, between A and B, and behind A. So this is an example for qualitative partition of the space. We hope this approach will be less sensitive to noise because errors will be ignored by the qualitative inference. And also it's going to be, we hope it's going to be low on complexity, easy to compute on low compute platforms. So the concept in general, as we talked about, we are using very small two landmark SLAM problems. Okay, we are not going to use a global frame to infer what we want to know. And also we are going to use qualitative spatial partitioning, qualitative geometry. So there are many types of partitions. For example, the left-right, the double cross we saw before, and there are many other partitions. It doesn't really matter. We can choose anyone according to the application. So for example, if we have a camera that sees these two landmarks, we can infer that the camera is in this qualitative state, okay? And in the camera, if the camera moves, it moves to a different qualitative state, and so on. So this is I just want to show you how qualitative localization looks like. So on the left side, we have like the red circle is a camera, and it measures 4 landmarks currently. It only sees these 4 landmarks. And then on the left side is metric localization. Okay, we can infer the localization of the camera metrically, and that's it. On the right side, we are using the double cross partition. And then the camera is on like this qualitative state, right? Between 10 and 8, and on the left side of them. And because we see more landmarks, we can have also the qualitative state of the camera in the 7 and 8 frame, okay, which is this one. And we can use like all the qualitative states that we can actually infer at this moment, and then interject them and get an accumulated qualitative state, which is the general qualitative state of the camera. So when the camera moves, you can see the relevant qualitative state. This is a ground truth. Okay, this is not inference. I'm just showing the difference between qualitative and metric navigation. Okay, so how does mapping look like in this framework? So the way we do mapping is we just take landmark triplets. Each time we see 3 landmarks together, we make a frame of reference from 2 of them, and then we try to infer about the 3rd landmark, if it's on which specific qualitative state it's on. Okay, so if we see these 3 landmarks, we get an inference, and then if we see these other 3 landmarks, we can make another inference, and so on. And sometimes these local frames are connected with the probabilistic factors, which enable us to move data, propagate data between different triplets. So this whole concept is not new. We are not the first ones to think of it. It's actually qualitative spatial reasoning is researched for at least 30 years, but the first like full framework, the first like meaningful framework for SLAM was introduced in 2013 by Cornell. They made a work for the Mars rovers, and then they made a SLAM framework, qualitative SLAM framework, but they just mainly used mapping and not localization. And also their work is not probabilistic, okay? It's just a feasibility test if a specific qualitative state is possible or not possible. Then after that, there was more research in Cornell talking about the probabilistic formulation of this problem, and also trying to think about active planning. And in addition, there's another research in this in ANPL in our lab by Itai Zilberman, which is also addressing active planning in this qualitative framework. And he also talks about composition. We'll soon see what composition is. So just to sum this up, we'll talk about our approach, what we actually do in this research. First of all, we make a full probabilistic SLAM framework. Okay, we're doing localization as well as mapping. We incorporate more types of measurements into the SLAM problem. For example, motion model was not used before, and we are doing it now. And we also show how to represent the map in a factor graph and how to propagate data between different local frames in the map. So part of this work is published in IROS 2020, and the rest of it will be published in a journal, and also we'll make available an open source repo for this type of inference. The benefits we actually did achieve in this research, if you compare it to state-of-the-art qualitative spatial reasoning, we improve accuracy as well as running time, just because we use like other types of measurements in SLAM. And we also show how to estimate sets of landmarks that were never seen together, were never actually measured by the camera, which is an important step for active planning. When comparing to traditional SLAM, still our method is like very low compute, and it should be robust to noise, and also uses a very simple computation process. So we hope it's going to be effective for low compute platforms like drones and like small autonomous platforms. So we just now try to talk about the actual specific things we did in the research. Now we are going to talk about single triplet. Okay, so we said we are estimating separately each triplet of landmarks, and we are using a relative coordinate frame, and then we fuse the data in a factor graph, in a map, okay, between these triplets. So when we look at a single triplet, some annotations, we assume the camera measures this triplet several spots in time for several time steps. And then the location of the camera, the pose of the camera, the metric pose in this AB frame is denoted as X for each time. And then the triplet ABC is a notation that means the state of landmark C in the AB frame. So L is the metric location of the landmark, and S is the qualitative state of the landmark in this frame, okay? H is the measurements we have until time N, and then what we try to infer is the probability for landmark C to be in each qualitative state in the AB frame given the measurements. Okay, so this is the single triplet problem. We are using in our research azimuth measurements. So the camera just measures azimuth to the 3 landmarks. And then also heading, like we get a heading measurement between 2 camera poses, okay? So it's not a complete motion model. It's much simpler, easy to implement in simple platforms. And then that's it. So our method is like incremental. You can improve the estimation as you get more measurements, and that's it. So you have like measurements to the landmark, azimuth measurements to the landmarks, and then heading measurement between camera poses. And the way we do it, we just solve the small 3 landmark SLAM problem metrically. Okay, so we solve the metric problem and we get a probability distribution for landmark C in this AB frame, metric distribution. Okay, and then we just integrate this distribution over the qualitative state, and we get a qualitative probability, qualitative state probability. So this is a very simple way to solve this problem. If we look at the formulation for this problem, is just trying to solve the probability for a specific qualitative state of C in the AB frame, given the measurements. And then you can see that we just solve the metric problem itself and just integrate over different states, okay? So the metric SLAM problem can be, this is like a standard SLAM formulation. It can be developed to be like a collection of factors, each one showing like a different probabilistic connection between camera and landmarks, camera motion model, and so on. So the thing is, we are not going to solve this in the standard traditional way using like Gaussian variables and so on. We're going to solve it in a little different way, and I'll show later why this is good for this for our research. So I'll just talk about the geometry of the problem a little bit. It turns out that if you have measurements to 2 landmarks, azimuth measurements from the camera to two landmarks, then you can infer that the camera is located on a specific circle, a part of a circle. Okay, this is called the locus circle. And if you have like 2 poses of camera, okay, the camera is located here and then it's located here, and you have measurements for A and B landmarks from these 2 poses, then you can infer that the camera is on 2 locus circles in 2 different times, okay? And then because you have also a measurement to landmark C, you can just triangulate and get the specific location of landmark C in the AB frame, okay? The thing is that we don't know where the camera is located on the locus circle, okay? So that's why we have, like, instead of getting a specific location for landmark C, we just get a curve that it can be located on. Okay, so this is when you have 2 views. When you have 3 views, you can actually triangulate the specific location of landmark C, and it's like fully constrained. So this is the basic geometry of the problem. The way we solve it, we don't use like a Gaussian inference, like the standard Gaussian inference. We just use a sample-based approach, okay? So given x1, like the measurement of camera 1 for A and B landmarks, we just sample the location of the pose of camera 1 on this locus circle, and then we sample the pose of the second camera on the second locus circle, and we also assume measurement noise. So the sampling is going to have some thickness. It's going to be like a sleeve around the locus circle. And we also sample the motion heading. Okay, so we have a reading of the motion heading from camera 1 to camera 2, and we assume we have some noise. So we make it like a little thicker. And then like for each, like we take all the combinations of these sampling samples, and then we just triangulate landmark C and get like C to be on this curve, which has some thickness now. Okay, the thing is that the number, this may look like an expensive way to solve this problem. The thing is that the samples, the feasibility of samples is greatly reduced when you have two views, okay? So out of all these samples, you have like very few samples left for two views, and then for three views of the camera, it's like very much reduced, and like you don't have a lot of samples left. This is why for this problem, this small problem, the sampling approach works well. So this is an example from our simulation. You see like 1, 2, and 3 is the camera poses, the ground truth camera poses in this scenario. You can see landmarks A and B and C. And like the green circles are the original locus circles for the cameras. The blue segments are the reduced, like the valid samples after you have two views. Okay, so you can see that when you have two views, you can greatly reduce like the location of the camera, the pose of the cameras, and then the green parts, like the green markings you can see next to the cameras, are the possible camera poses when you have three views. Okay, so it's like very much constrained, and you have like very few samples left. And then the location of landmark C triangulated from these three views is like the red line you see here. Okay, so when you have more views, it's going to be like very much constrained. So the reason we are using this method for estimating the SLAM problem is that it's like very simple, okay? So in regular SLAM, we have to initialize and then linearize variables because we assume the variables are Gaussian and they actually are not. So we have to make linearization, and then you have linearization error and stuff like that. And then you have to solve eventually. In our method, it's like very direct. You don't have any constraints or any like prior steps you have to take. It's very simple and very fast. This is why this fits to our like approach. So that's it for now. Okay, so actually, so far we didn't do much. We just solved a small 3 landmark SLAM problem, and we did it in like a weird sample-based way, and then we just integrate over the sampling, the sampled probability to get the probability for each qualitative state. So now I'm going to show you the reason we are doing this this way. We want to try to use the fact that we just estimate qualitative states and not the actual metric probability distribution to our benefit, okay? So we tried a few approximations. We are trying to make approximations to this method to do it faster and easier, and then use the fact that we just make probabilistic inference to take advantage of this approximation, okay, in a way that will not hurt the performance. So what we found out, for example, is that we can just neglect the noise. We just assume we don't have any noise on the samples, okay, and we sample on the actual locus circle without assuming noise, and we found out that the performance are very similar to the full algorithm, okay? So this makes the inference much faster because we have like many times less samples, and because we just care about the qualitative state and not the metric state, we found out that the performance are very similar, okay? So this is an example. We made a simulation, and what you can see here, like we use several metrics, okay? So each line in the table is a different metric to measure the performance. And then the baseline part is the state of the art, the Cornell method. And then you can see our algorithm and our fast variant of the algorithm, okay? So the different metrics are like the M.Sc is probabilistic correctness. It's just the probabilistic distance between the ground truth and our estimation. And then geometric distance is the same thing, but it takes into account the distance between qualitative states. Okay, so if two states are close, then the price is going to be low. And if the states are very far from each other, the price is going to be high. And then entropy is just the sharpness of the distribution. Okay, it's like how much information we have in the distribution. It doesn't care about the ground truth at all. And ground truth rating is like when you take the probability for each state, you can put them in order of the most probable to the least probable. And then on this scale, we ask ourselves, where is the ground truth located? Okay, if it's like the most probable is the ground truth, then it's a good estimation. If it's second, then it's like less, and so on. So you can see here a few things. First of all, you can see that we have like much better performance than the Cornell research, okay? And that's only because we incorporate motion model measurements. When you don't use motion model, you are much less constrained and get like lesser results. The other thing is that we are also faster than the original method. And this is because we can reduce the number of samples rapidly, okay? So our method in general is like better both when you talk about computation time and performance. But the other thing you can see is that when you compare to our fast variant, the fast variant has like a very similar performance to the full algorithm, but it runs like 2 orders of magnitude faster, okay? So this is a way to use the qualitative inference to our advantage. Okay, we found a way to sample much less and use a much faster algorithm, but get almost the same results. So this is how we show that qualitative inference is easier. Some more results of our research. We won't go over all the results, but when you look, for example, in the bottom right, in the M.Sc, like the probabilistic distance, you can see a few things. First of all, like we have better performance than the baseline. Okay, we saw it before. But the other thing is, here you can see like the x-axis is the azimuth noise. Okay, in our simulation, like we use a simulation of like many scenarios, about 10,000 scenarios. And so we use a different azimuth measurement noise in each scenario. And then we look at the probability error, okay? The y-axis is the error. So when the azimuth noise goes up, because our algorithm does not take azimuth noise into account, the performance go down. Okay, we have like the error is starting to get bigger, but we can notice that first of all, we are better than the state of the art anyway, and also that up to about 3 degrees of azimuth error, the inference gives like very good results. The results are really close to the ground truth. Okay, so 3 degrees of azimuth errors is like very high error, very high noise for camera measurements. Okay, so it means that practically, if you use a camera and even like not a very good quality camera, the azimuth noise is going to be like typically less than 3 degrees, and then you're going to get like really good estimation. Okay, so the conclusion is that for practical users, the estimation is going to be like very good, and this method could be practical. And again, the difference between our method and the baseline is just we added motion model. We added more types of measurements, and that's why we get better performance. We also used a data set by the Toronto University, and we got just, this is an actual data set. It's not a simulation. It's like actual robots with landmarks, and we got like very similar results. So it works in real environments as well. So for conclusion, we added a motion model, we got better performance and also better runtime, and we found a way to a fast approximation to use that uses the qualitative nature of our inference to make the algorithm much faster and easier. And also the general performance up to like 6 degrees of measurement noise are like generally good. So this was the first part of our research. We saw that this is like a feasible method and it could be useful. And we published it on the IROS 2020 paper. And now I'm going to talk about qualitative composition. This is a way to propagate data between different triplets. Okay, so you remember the map is made of like many triplets. And sometimes we want to, if we get a measurement for a specific triplet, we want to use this data to better estimate like other triplets. So I'll show you how it's done. It's called the composition. And like if we have a specific triplet and we estimate, like we have an estimation for the qualitative state, and then we have another triplet, and we want to infer like this triplet, the third one, A, B, D. Okay, so you notice that if these 3 triplets have, they're like using the same 4 landmarks, then there is a probabilistic connection between these three triplets, and we can propagate data. Okay, so we can estimate even if we never measured A, B, and D together, we can still estimate the qualitative state of landmark D in the AB frame using like the other triplets we measured, okay? So this is like the general formulation. We want to try to find a specific triplet state using measurements for this triplet and other triplets, or like in a specific case, we can also do it when this triplet is not measured at all, okay? So I'll just talk about how we make the map, how we just code the map. So we just use a factor graph. Many of you guys know about factor graphs. So it's a way to, like, it's a graph with 2 types of nodes. One type is nodes that are variables, okay, that can these are the variables we want to estimate. In this case, it's a landmark triplet, okay, the qualitative state of a specific landmark in reference to two other landmarks. And then we also have factor nodes. The factor nodes are probabilistic connections between these variable nodes, okay? And we have two types of factors. One of them is composition factor, the one we are just going to talk about, and then we have like prior factor. Prior factor means we just had the measurements of these landmarks, and then we have like a prior estimation about the qualitative state. And like some of the nodes may have a prior and some of the nodes may not have a prior if we've never seen them before. Okay, so how do we calculate the composition? So like if we have, because we viewed A, B, and C together, let's assume we have the metric location of landmark C in the AB frame. And then because we measured B, C, and D together, we have the metric location of landmark D in the BC frame. And then like it's very easy, like if we have, we can just concatenate these transforms and then get the metric location of landmark D in the AB frame. Okay, so in the same way, after we have this metric location, we can also like infer the qualitative state. And if we have an error, we're going to integrate it over the different states and so on. So this is how composition works. Okay, so the underlying problem behind like qualitative composition is the metric composition, which is very simple. So again, we are not trying to solve the metric problem. Okay, this is just the underlying problem, but we are trying to use the fact that we only need the qualitative state to our benefit. So we're going to make another approximation. Generally, we're trying to estimate the qualitative state of a specific triplet of landmarks, given the history of like all the other triplets, right? In this case, the two other triplets. So we are going to make an approximation and we are going to forget about all the measurements we have and just remember the estimated qualitative states of these two other triplets. Okay, so this is not an accurate inference, it's approximated, but it's going to be much easier. Okay, like if you do some algebra from this problem, you can get like this formulation. And I'm not going to explain how we got to it, but I'm going to explain the meaning. So the meaning here is that we have a part that is like the metric part, which integrates the actual metric locations of the two given triplets is entirely independent on the history, okay? So this is because we made this approximation. It means you can calculate this part offline, and then you can just integrate it over different, like all the combinations of qualitative states of like triplets 1 and 2. And that's it. Like you can do this whole part, the metric part offline. You can calculate a box like 20 by 20 by 20, n by n by n. Okay, if you have n qualitative states for each triplet, you can calculate all the options for these three different states. You can calculate the probability for all these options, and then you can just take the prior, like take the probability estimating these two given the two prior triplets, and you can just multiply it, and that's it. So it's like very easy to calculate. The main stuff is done offline, and then it's going to be very easy to do online. Okay, so this is again an approximation that uses the qualitative nature of the problem, and we are going to see how good this approximation is. Okay, so like this part, the way to do this approximation and the way to do composition is also published in the IROS. And now I'm going to talk about the last part. And we are going to show how this approximation, how much data does it propagate through a graph, okay? Through an actual factor graph. Okay, so you remember that the factor, the composition factor, is now approximated. Okay, it's like a lighter factor. But when you have this factor graph with all these factors, and if you have measurements for some of the triplets, you want to propagate the data through the graph. And there are rigorous algorithms for how to do it. So the way to do it, like the accurate way, is by elimination. Okay, you just somehow take all these landmarks, these two factors, okay, and just replace them by one factor of many landmarks. The problem is that because we are using deterministic inference, this is going to be exponentially more expensive. And we actually try to do it using GTSM. GTSM has ability to solve discrete factor graphs. And we saw it's like infeasible. It takes too much time. So instead, we are using a different algorithm. We are using a greedy algorithm, which is like influenced by message passing algorithms. So message passing algorithms is a way to propagate the data to all the nodes in the graph, but it works well when the graph is not loopy. It doesn't have any loops. When the graph does have loops, it's not, we don't know how good this algorithm is. So we took an even easier, even a simpler algorithm. It's greedy. It starts from source nodes. The source nodes are the nodes that have prior, that have current estimation. And then we are trying to propagate data to all other nodes. So the algorithm is going to go through each node only once. When it's like calculated, then it's not going to update this calculation again. And it's going to take the best single path from the sources to each node, okay? So each node is going to get information from the most informative single path from the sources. So that's a simple algorithm. Just for this algorithm, we use something called information score. The information score is, so you can ask like, what is information? How to represent the information in each node? The way to do it is like looking at the entropy, but entropy is not a convenient size to look at because it's not bounded. So we take something called information score, which is basically the difference between the entropy and like uniform entropy, which is the maximum entropy, and also normalized in reference to the minimum entropy, okay? So the minimum entropy is the inverse of information. If you have a perfect inference, you know exactly which qualitative state is correct, then you get the minimum entropy, the most information and minimum entropy. And if you don't know anything and you have like a uniform distribution, then you have the maximum entropy. So we just normalize the distance between our specific entropy to the maximum entropy. How far is it from uniform? And that's it. That's the information score. We call it information score. And this is the value we propagate through the graph, okay? So an example for how this algorithm works. So in this simulation, we have like 3 landmarks with 3 triplets with information. Okay, we saw them with the camera. We have inference about their state. And then at each step, we take the most informative, like we try to propagate data through the factors. These 2 factors, we saw that like the propagation is less informative. They get like a lesser information score. So we took just the one that was most informative and forgot about the others. Then for the next step, we assume this is also inferred, and then we are doing it all over again. We're trying to get the best factor that is available for propagation. And then we find the one that is most informative and so on. And this is how we get to the whole graph, okay? So it's easy to show that this way, each node gets the best single path propagation. Okay, so now we have a simulation. Like this is an example from our real simulation. We have a simulation, we can propagate data through the graph, and we want to know how good is the composition, how much data did it propagate, okay? So we can just look at at all the nodes that didn't have measurements in the beginning, and then see the information score for all these nodes. And we can just, for example, look at the mean, okay? But the mean is uninformative. I can't give you a number and tell you like it's propagated half of the data because you won't learn anything from it. So we're trying to see how data is propagated relative to the topology of the node in the graph, okay, and how much information we had. So this is why we define something called the composition level. A composition level is a tool for us to characterize for each node how is it topologically located in the graph. And then we are going to look at the information score and see if it's correlated to the topology in the graph, okay? So what is the composition level? The composition level is actually the information score for observed nodes. And then for unobserved nodes, we propagate the information score in the graph, but we don't use real composition to propagate. We just assume the information score is going to decay. Each time we propagate it in the graph, each time it goes through a factor, we're going to assume it decays in a specific amount each time, and that's it. And this is going to give us some way to look at the topology of the node in the graph. Okay, so what we got eventually is that you can see like here on the x-axis, you can see the composition level. It actually means where a node is located in the graph, how far is it from the actual measurements we made, how much factors do you have to, how many factors do you have to go through to propagate this information to this node. Okay, so nodes with low composition level are far from the initial measurements, and nodes with high composition level are close to the initial measurements. And then the y-axis is the information score, the actual information score of the composition, like the full composition itself, okay? So we see a good correlation. It means that if the nodes are far from the actual information, they are going to get lesser information when you actually do the composition, and vice versa. Okay, so this is a very good result. It means that we understand how the composition works. Okay, so we understand that it just more or less decays every time it goes through a factor. If you go through one factor, then you still have like a lot of information. If you go through like a few factors, you still have information, but if you go too far, then the information is going to decay and you're not going to have information in your estimation. So this is another important conclusion of this research. So the conclusions of this part are, as I talked about, we know how composition is propagated. It propagates significant information, okay? And if you go too far, it's going to decay. But the thing is that we see that it's practical for active planning, okay? You can actually estimate unseen nodes, nodes that you didn't measure together at all, and still estimate the qualitative state of this landmark triplet. And this is a big step towards active planning. You can plan for landmarks, triplets that you haven't seen together yet. And this part is not yet published, but will be published soon. So when you have an overview of the research, our main conclusions is that the general performance are good. Okay, if you have reasonable measurement noise, you get like really good inference, which is very close to the ground truth. The complexity, like the computational load for using these methods is very small. It's practical for low compute systems like drones or other like very low power computers, and it might open the way for fast active planning. Okay, so today active planning in traditional methods is very expensive. You have to get a lot of time and a lot of computing power to plan a path. And using these methods, it could be like very easy and very fast. Again, we are just inferring qualitative path planning, but maybe it's enough for some robotic missions. So things we can work on in the future concerning this framework. One is like rigorous graph propagation. Okay, we just use an heuristic way to propagate data through the graph just to learn how composition propagates and if it propagates enough data or not. But we didn't find like the best way or an optimal way to propagate through the graph. Another obvious research direction is active planning. Okay, using all this framework for planning for autonomous systems. And then you can also expand this work on the basic level for handling like complex landmarks. So we handle only point landmarks, but if they have volume, then you can find a way to do it. And you can try to take into account data association. Okay, so we assume we know the association. It means that we know which landmark we see at each time, but if there are association errors, there are ways to correct these errors and to cope with them in this framework. This is another line of research. And then you can also go to 3D geometry and so on. That's it in general. This is the conclusions from our research. I think in general, it's a very important research. We found another way to do SLAM in a very different and in some ways easy approach. And I hope it's going to be effective and usable for someone in the far future.
Thanks, Roee. Thanks very much. So we have time for one or two quick questions from the audience, if any. Going once, going twice. No questions.
Question.
Yeah, Leo. Go ahead, Liran.
What about 3D?
So generally, 3D geometry is going to be like more or less the same. I think like the geometry itself is going to be different, and the way we do the sample-based approach to solve the metric problem, the small metric problems, is going to be different. It's going to be, someone is going to have to rethink about the specific algorithm. But generally, the approach, I think, is going to be the same, like graph propagation and how to define the variables to estimate is going to be similar. And just the algorithms might go through a bit of a change.
But as of you spoke about future work, you think 3D is less important than the other future works that you spoke about?
I think that if you want to take this approach and use it in real world, you have to do all these things noted here. Okay, you have to correctly handle 3D. You have to correctly handle data association and landmarks that are not points. All these topics will have to be like implemented and researched a bit more to make it usable for actual autonomous systems.
Yeah, so many exciting possible directions here. More questions? Okay, so Roee, thanks so much. That's all. Thanks, Roee, and see you next week. Next time, not next week. Sorry, next time. Thanks.
Thank you, guys. Have a nice holiday.
Thanks.